Math 2414, representing functions as power series, video 9, sixth example, one to memorize eventually. I'm not kidding. As you move forward through calculus and beyond, you're expected to know the power series for arctangent of x. In fact, you need to have it memorized by the end of this chapter. It is a very common one. All right, so no big surprise here. We're going to find the power series for f of x equals arctangent of x, and we're going to determine the interval of convergence. The game plan that we've been playing out so far is to try to take a function and associate it with something that has this structure. Because if we have that structure, then we can rewrite the function as the series, the sum from n equals 0 to infinity of a times r to the nth power, when the absolute value of r is less than 1. And the tricks that we have at our disposal now are derivatives and integrals. So, do you know the derivative of arctangent? You should. Let's take the derivative of arctangent. So we're going to start this journey by taking the derivative. Guess how we're going to end it? By undoing the derivative. So at the end, get ready to integrate. The derivative of arctangent is 1 over 1 plus x squared. And I believe we did this in a previous video, but we're going to redo it because you won't always be able to say, oh, I already did that problem. To get the correct structure, we're going to rewrite the plus as minus and negative on the bottom so that we can identify the first term as 1 and the radius as negative, the ratio is negative x squared. Yeah, we definitely did this one because I remember saying that when we have the absolute value of negative x squared is less than 1, because I remember drawing the parabola, that means that x is between negative 1 and 1. So that will be our interval of convergence for our series for arctangent, but we will have to check the endpoints as well. But let's go ahead and build our series. Sum n equals 0 to infinity of the first term, which is 1, times the ratio to the nth power. And it literally just dawned on me in other videos when I was saying you want x to a power, not x with a bunch of junk to a power, to make it look right. Well, also to make it easy to integrate and differentiate. All right, so let's do that. Sum n equals 0 to infinity. The 1 in front doesn't matter, it's just 1 times. We can split the negative off by giving it its own exponent. And then we would have x squared to the n, which is x to the 2n. So now that we've differentiated our function and got the series for the derivative, we just have to go backwards now and integrate to get the series for our given function. Let's just do it in one move. We're doing an indefinite integral, so let's start with our constant. N equals 0 to infinity. We have negative 1 to the nth power. And now when we take the antiderivative, we're going to add 1 to the exponent and divide by that new exponent. Well, that was pretty painless, but we're not out of the woods yet because we still have 2 things to do. Number 1, investigate the endpoints of the interval of convergence to see if we picked up convergence at either 1 or negative 1. And number 2 is to find the value of that constant. Let's start with finding the constant. We have arctangent of x is equal to the sum n equals 0 to infinity of negative 1 to the nth power over 2n plus 1 times x to the 2n plus 1. Our interval is still between negative 1 and 1, which is equivalent to saying it's centered at 0 and has a radius of 1. Let's check x equals 1 first. I'm sorry, I meant to find the constant of integration first. But you know what? The convergence of the series doesn't depend on the finite beginning. It depends on the infinite end. So we can go ahead and check for convergence now at either 1 or negative 1. But let me make a note here. to find C. So hopefully I won't forget to look at that. All right, so at x equals 1, we have arctangent of x, arctangent of 1. We're not evaluating arctangent. We are checking convergence of the series. Sum n equals 0 to infinity. If we put in 1 for the x, we get all this, and then 1 to the 2n plus 1. But I feel silly writing that because 1 to any power is 1. So we have n equals 0 to infinity of negative 1 to the nth power over 2n plus 1. This is an alternating series. That really is an alternator with a horribly drawn n. There we go. But since it's an alternating series, we can check the alternating series test, which says to look at the term without the alternator. So just remove the alternator and then see if it's positive, decreasing, and approaching 0 for n equals 0, 1, 2, 3, et cetera, et cetera. Well, this is clearly positive. The top's positive, the bottom is positive as long as n is 0 or greater. This is clearly decreasing because as the n gets larger, so does the denominator. Denominator approaches infinity while the numerator stays at 1. And this does approach 0. It is possible to decrease and not approach 0, but in this case, it does approach 0. Satisfies all 3 criteria for the alternating series test, and so we can say that this converges by the alternating series test. Converges by the alternating series test. Let's check out x equals negative 1. Sum n equals 0 to infinity, negative 1 to the n, put negative 1 for the x here, and get negative 1 to the 2n plus 1 over 2n plus 1. And I know what some of you are thinking from the last video. Haha, you're trying to trick me into saying there's an alternator where there's not one. Well, maybe or maybe not. Let's look at it a little bit more closely. That guy is not an alternator. Its exponent is always odd, which means that is always negative 1. So we get the sum n equals 0 to infinity, negative 1 to the nth power times negative 1 over 2n plus 1. But now we have negative 1 to the nth times negative 1. So we can add the exponents there and get negative 1 to the n plus 1, which is still an alternator, 2n plus 1. We could have also pulled the negative 1 in front like that and left the exponent alone. There's a couple of ways that you can handle it. But right now we're just checking for convergence. This also converges by the alternating series test. Because without the alternator, it's the exact same term as it was before. The only difference between the alternator here and the alternator there is that they shift places. The first alternator, this one, starts out positive when n equals 0. This alternator starts out negative when n equals 0. So that's the difference between those two alternators. They're still alternators. One just starts positive, one starts negative. But both series converge by the alternating series test. So we pick up convergence on both ends of the interval. Oh, don't forget that. So we have that arctangent of x is still equal to some constant, which we haven't figured out yet, plus the sum n equals 0 to infinity of negative 1 to the n over 2n plus 1 times x to the 2n plus 1. But now we can say that the interval includes negative 1 and 1. We could also use interval notation like that. Negative 1 to 1 with brackets on both. To find c, we just let x equal some number in the interval. I recommend the center, which is 0. We get arctangent of 0 equals c plus. Putting in 0 here will zero out every term. So we get a big O c plus 0. Arctangent of 0 is 0. And c is equal to 0. Oh, look, we got c equal to 0 again. So now we can wrap this up and confidently say that arctangent of x is equal to the sum, n equals 0 to infinity, negative 1 to the n over 2n plus 1 times x to the 2n plus 1 on the interval negative 1 to 1. By the way, if you were to expand this series, I'm going to do it on the next page. I'm going to write the sum up here just so we can see it. Starting at 0. If you were to expand this series, when n equals 0, you get 1 over 1 times x to the first. When n is equal to 1, you get negative 1 over 3 x cubed. When n is equal to 2, you get positive 1 over 5 times x to the fifth. When n is equal to 3, you get negative 1 over 7 x to the seventh. And now you see the pattern emerging. Plus 1/9 x to the 9th, minus 1/11 x to the 11th, and so on and so forth. Now, I want to show you one more pretty cool thing here. But you have to remember that tangent of pi over 4 is equal to 1. Because if tangent of pi over 4 is equal to 1, then arctangent of 1 is pi over 4. So in other words, if we let x equal 1, because we already got convergence, arctangent of 1 is pi over 4. The series on the left becomes 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11, so on. So the alternating harmonic series that goes 1, negative 3, 1/5, negative 1/7 plus 1/9 minus 1/11, and so on, converges to pi over 4. In fact, if you wanted to multiply both sides by 4, you could say that this is an approximation of pi. And you would be right. Yay, math.